Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's a pleasure to welcome Adam Tripala from MIT. I think many of you know Adam and his work on using Coq to prove various things. And we had the pleasure of having his student Jason intern with us in the summer. Sorry? Yes, I'm sorry, yes, of course, as well, and Peng. Yeah, Perry. So Adam's going to talk about his Bedrock system, which is a framework for doing everything, so it seems. So thank you, Adam.
Thank you. So I'm going to be talking about Bedrock, which is a system we've been building inside the Coq proof assistant. And I want to start out by setting the stage for the general kind of problem that Bedrock solves. So in theory, all the things we do with computers we could do by building a new piece of hardware for every program, but that's no fun at all. So of course, we'd rather be using some sort of universal computer. We'd like Turing-complete systems, but we're not done yet because Turing machines have this problem that it's hard to achieve very good performance running things on Turing machines. So we rely on modern hardware platforms that have assembly languages with efficient implementations. And this also is not good enough because if we all had to write all of our programs directly in assembly, we would never have nearly as interesting programs as we do today. So we really depend on ecosystems of software development tools that provide higher levels of abstraction. Now, in particular, what those ecosystems provide is a number of different good things. We might put in a few different categories, potentially with some overlap. I'm not quite sure of the boundaries in particular between the first two here, abstraction and modularity. And in the abstraction category, we have things like structured programming and abstract data types. They're sort of ways of thinking about programs at a higher level of abstractness and, for instance, viewing a complex implementation through a simple interface. And we also care about modularity, or ways of helping us break a big problem into smaller problems and get some guarantees about the way in which the pieces will come back together again. And examples of this include safe type systems and garbage collection, where you don't have to think about memory management. And also another important pillar of programming today is automation, where, for instance, we rely on compilers to translate from some of these high-level abstractions to lower levels. And there are a number of other things that you might also call compilers, but are also referred to by other names like linkers and code generators. So we need all of these in our ecosystem to be able to build the things we build today. Yeah?
Performance? Would you stop it in there or another pillar?
I'd say it's sort of an orthogonal dimension, but all of these elements, or many of them, are in support of performance, and we wouldn't need them if we didn't care about performance. All right, so concretely, how does one of these tool ecosystems look? Well, at the bottom we have a machine language, which is what the hardware knows how to run. We might write our programs in some mid-level language. I'm sort of thinking of that as like a C style of language. And we have a compiler that knows how to lower the mid-level language to assembly, and an assembler that knows how to turn that into an object file. And an important thing here is that there's a standard format of object files that many different tools can produce for us. And we might have a whole other language with a similar pipeline that leads to object files in the same format, and then a linker that knows how to combine these together into one machine language program. We might also prefer to write in a higher level language and have a compiler that plugs into this pipeline, perhaps through one of these mid-level languages, and we might link in a runtime system written in that same language. And we might even do things like use a parser generator and have a declarative description of a program and a code generator that translates it into some other part that we have implemented in this pipeline. So all these pieces are essential to the kinds of software that people are building today. We might also consider having a common type system throughout this picture. For instance, in the CLR system with a language of types that applies to bytecode in the end, but has consequences that are pushed back through the rest of this diagram. And now we have sort of a fixed abstraction and modularity discipline that all the levels of this picture need to respect. and that's a benefit for understanding libraries and so forth. So the first picture, let's call that L0 for bare assembly language, and then we can add conventional types into that picture and arrive at L1. And of course, it's interesting to ask, as n approaches infinity, what is the limit of this sequence of languages where we're adding more and more expressive abstraction and modularity features into the core of everything? Obviously, the limit is distributing assembly programs with proofs of functional correctness. So if nothing else, it seems like an intellectually interesting thing to study. So let's see how this might work pragmatically. So why is this worth doing? Well, one reason is that it's good to know that our programs are correct. So obviously, it's a good thing to have rigorous proofs of software correctness, and therefore, we'd like to have the tools that help us build those proofs more easily when we've constructed programs in the way that we're used to building them. But there's another reason that I find maybe even more exciting than that one, which is that maybe we can use formal methods throughout the programming process and enable new kinds of abstraction and modularity that we wouldn't have been able to get to work otherwise, because some programming tasks might just be too hard for people to understand when they have relatively weak notions of interfaces and abstractions. So hopefully, by applying formal methods, we can actually lower the cost to build the program, not just say, this team's going to build it, and then this team's going to prove it correct. As a bonus, let's try to make those two processes into one. And here's sort of a restatement of that hypothesis that by using formal methods, we can come up with superior interface formalisms that help people understand complex tasks in new ways. All right, so in particular, I want to do this inside of the Calc proof assistant, where we have an assembly language at the core of things, and probably most of you are familiar with the work that Benton and Kennedy have been doing here about sort of what happens below the assembly language point in this picture, and also some parts above. But let me focus on describing the things that they're doing that we're not doing in the Bedrock context. They're dealing with semantics and verification for machine language, working with popular instruction set architectures in detail, and verifying some of the lower level tools like assemblers and linkers. So these are all important things to do. And there are also complementary benefits at the top of the picture. What we're working on in our system, which is called Bedrock, it's also a library inside the Calc proof assistant. It supports modular verification of code libraries. We've done some work on extensible low-level languages with verification support. We've done verified compilers for sort of C-level languages, for domain-specific languages, and also we've done some work on deriving programs from their specifications. So we're sort of trying to fill in the higher levels of that picture of a software development ecosystem. But like in the work going on here, Bedrock is for programming and verifying and compiling all inside of the Calc proof assistant. You don't have to step outside of that world until you actually have your final program and you'd like to actually run it on real hardware. Then we have to export to the outside world. But everything else goes on inside of the proof assistant.
So you're writing your compiler in Calc?
Yes, compiler is plural.
Compiler is?
Multiple compilers inside of Calc.
Many
Yeah.
compilers, all live in Calc. Okay.
Yeah. Writing and actually running them inside of Calc, not extracting to OCaml first. Yeah.
Do you consider assembly language to be sort of a class of things, or one particular one, or sort of?
We have a particular one. I also think of it as a class of things.
Okay. I mean, what does it take to be an assembly language? I mean, does that matter, or do you just sort of take intels and fudge it a bit, or take arms and fudge it a bit, or? I mean, how is the assembly language different from C?
If it has local variables, it's not an assembly language. That's one necessary but not sufficient condition. And I could try to go into more detail, but I haven't thought of a concise answer ahead of time, so maybe I'll put it on the back burner. Okay, so we had these three pillars of effective software development ecosystems, and all of these are going to come into play in Bedrock. We care about abstraction, and this takes forms like abstract data types with semantics, with specified interfaces of how the data type is supposed to behave. The general idea of specifications in higher order logic to provide interfaces to components, and many other parts. On the modularity column, we have program logics, and semantic linking, where we want to verify libraries separately and then combine both the code and the proofs to provide a theorem about a whole program. And in the automation category, now we can have not just automation of compilation and programming, but also of formal proof generation. And we apply this automation both at the very lowest level to proving pointer-based programs correct, and also at a higher level to derive programs from specifications. And I'll say more about each of these pieces as I go. But really, I'm going to skip a lot of elements in this talk that are sort of well known in the community at this point, but weren't at all well known, say, 15 years ago. Basically, the challenges of how you verify programs that deal with mutable, recursive, higher order data structures using impredicative quantification over specifications, and do it all in a modular way that supports separate verification of libraries. And we actually want to implement this in Coq, so we'll need nice notations for programs and specifications, and we'll need good ways to automate the proofs about these programs. Each of these points is non-trivial, but I want to focus on some other parts of the picture for this talk. But we have stories for all of these. In particular, just a quick example of a verification that we've done using Bedrock. This is a diagram of the modular decomposition of a cooperative multi-threading library. And each of these dashed borders is an encapsulation boundary where there's some private state inside the border, and code outside the border can only get at that state by calling the exported methods of that module. And each of these methods has a specification. So in particular, at the bottom here, you can see maybe the most interesting part of this diagram that is a 4 levels deep nested encapsulated thing. The outermost one is called the scheduler, which is the main module that controls waiting for I/O events and waking threads up to respond to them and letting threads suspend themselves again. And it has a set of file records describing the open network connections that this library knows about. Each network connection has associated with it a queue of threads waiting for input on that connection and a queue of threads waiting for output. And those two, say the in queue and out queue arrows, point down to this next encapsulated component, which is the thread queues component. That is the idea of a set of queues that support NQ and DQ. And each of these queues is itself using a separate thread queue object, which is implemented in terms of the traditional queue data structure. And the queues here are storing the program counters and stack pointers of the suspended threads. So these are recursive, mutable, higher order data structures, and each of these levels exposes just the right kind of abstraction for its specification. So in particular, code outside this library sees the, say, receive from socket function. It's just a regular function with a specification that hides the fact that the thread might be suspended into a data structure instead of just having the function return normally. And this is all implemented, specified, verified, and compiled to assembly inside of Coq. And what we use this library for is a case study of running code on autonomous vehicles where you have a variety of interesting things plugged into a little robot like that one. There's a joystick potentially sending messages remotely, and somehow those messages should influence what the wheels are going to do. And so we've built this server that drops into a popular robotics platform called ROS, Robotics Operating System. And this is a server that's basically like a name service that helps the different components find each other's network addresses. And so the different physical things connect to the processor, and we rely on a set of non-blocking system calls for network access, which we're not verifying. We'll assume those are given, and we'll assume specifications for them. Then the thread library is built on top of that. This library provides blocking abstractions, which are more convenient to work with. It also relies on a memory management library. And a number of threads are running, handling requests from the different nodes of the system. They're connected to an in-memory relational database, which will store information like the address of the node that knows how to handle turn wheel requests is 1.2.3.4 or something like that. And so the joystick can ask the server, where do I find the wheels? And the server says, here's the address, and the server can connect to the wheels and start sending them commands. So everything above the non-blocking network syscalls box is implemented and verified in the Bedrock system. Okay, so let me say a bit more about exactly what we're assuming and what we're providing, what the theorems that we come up with are. So we're running on top of the Calc proof assistant. I've put the Calc logo in the trusted side of this diagram to indicate, as usual, we will assume that Calc is giving us correct answers. We ask it, does this proof really establish this theorem? On the untrusted side, we have a kind of semantic module system for assembly language where we have packages of code, specifications, and proofs that the code meets the specification. And in general, we will have many of those in one program, and we need to be able to compose them together. And we do that using a module system which has a soundness proof in Calc, so you don't need to believe in the soundness of that system. And what that will allow us to do is take a set of modules, compose them together, let one module satisfy the dependencies of another until we get to a closed assembly program that is no longer importing any more code labels from others, and a proof that this module meets its specification.
So somewhere in this diagram there should be the specification for the overall closed thing. That might or might not be what you actually want to prove, because it's quite hard to write specifications, is that?
It is. It is pretty hard, yeah. So in this case,
this kind of trusted piece in a way.
Right. The specifications of composed modules are computed from the specifications of the inputs, so you don't have to write it over again. But you might want to inspect the output to make sure it was computed in the way you expected.
I just meant that the specification of the closed assembly program.
Well, the way it works is that each function has a specification. So when you link two sets of functions, you get a larger set where each function has the spec from whichever input provided that function. There's no new specification that is sort of an emergent phenomenon of linking. It's just the union of the function specifications you started with.
So maybe I have to ask a question like this. Closed assembly program plus proof appears on this slide. What is it a proof of?
It's a proof that every function satisfies its specification in terms of a precondition and postcondition.
You don't have a big
there's no
theorem
overall
that says
theorem.
the robot behaves itself.
Yeah.
I think is the point.
Right, we don't have that yet. And indeed, we're not saying anything about interaction with the physical world. We're only, for the moment, modeling this internal state of the machine.
So each screw behaves as screw should behave, each nut behaves as nut should behave, but whether you put it all together you get anything useful is not part of your scope.
It's an interesting question. I guess to me, I feel like the specification style that we're using tells you something about the program overall, because a bug in one function could easily break the state that another function depends on, and you have to prove that that interaction doesn't happen in a bad way.
It suggests the words structural integrity as describing what you're checking.
Okay, I feel like that might suggest a weaker notion than we're actually implementing. We are proving functional correctness. It just looks a little different maybe than people are used to seeing because we're at the assembly level and there aren't as many abstractions built in.
So can your modules depend on each other, or are they
Yes,
linearly ordered?
there can be arbitrary recursive dependencies across modules. Every module has a list of imports of functions and specifications from others. All right, so once we have all this stuff in the untrusted part of the picture, we can throw it over the wall into the trusted part where we have a formalization of the syntax and semantics of an assembly language, and I'll tell you which one in a moment. And we have to choose some safety property that the final program should satisfy. This is actually done in a generic way based on the specifications of the functions. Basically, think of it as every function's precondition is always satisfied when you call that function. So ask Calc, do you believe all these together? Do you believe that this program has this property according to this semantics? And that's the basic operation of checking a program. And then we also have a traditional compilation toolchain, everything that happens after producing assembly language. We assume is given to us, and for the moment we're not proving anything about it. So here's our assembly language. Here's one example of what I apparently mean when I say assembly language. It's not too interesting, but I think if you take the time to read it, it won't be surprising. We're working with 32-bit vectors, and we have a small finite set of registers and addressing modes and operations. And at the bottom, we have a code module is a list of blocks of code, each of which has a label. It's a basic block, so it has a set of straight line instructions followed by a jump instruction. Jumps include indirect jumps via expressions and also conditional direct jumps. So it's one of the many small Turing-complete languages you could come up with if you wanted to actually be able to compile it easily to any of the common assembly languages today and run things with reasonable performance, which we do in this case, translating to 32-bit and 64-bit x86 and ARM, and maybe we'll be inspired to add some more in the future. For now, no proofs about those translations, but I think this really is an assembly language. It's not like an LLVM IR kind of language. It has a very direct kind of macro expansion translation to all of the popular assembly languages. So then this semantic module system that we put on top is called XCAP, or it's a variation of XCAP, which is a system suggested by Ni and Xiao in 2006. And so the notion in this framework of what is a whole program, it's just a set of basic blocks. Every basic block has a set of straight line instructions ending in a jump, and it also has a precondition, which is a specification in higher order logic of what the memory and registers should look like every time we reach this location. So a program is a set of such things. And the correctness condition is that when we run the program, every time we reach a basic block, the precondition of that block actually holds. So by picking rich enough preconditions, you can encode all kinds of functional correctness properties, or you can choose to encode type safety kinds of things. It's up to you. And then this notion of modules is that a module is a set of code blocks, each of which has a specification or a precondition. And the proof obligation of a module is that if some assumptions that we make about certain code labels existing in other modules with specifications that we give, if these assumptions hold, then in any whole program that includes this module, we will never be responsible for breaking a precondition. All of our preconditions will always be true as long as no one jumps to us without satisfying the appropriate precondition of the block that is jumped to. And finally, there's a semantic linking operation that takes two modules, combines them into a bigger module that includes all the code labels of the constituents and also connects together the proofs in the appropriate way, and will also remove imports that were present on one side that have now been satisfied by the exported labels of the other side. So by repeating this operation, we can converge towards a closed program with a proof that basically all of its assertions will always be true whenever they're reached.
You said precondition a lot, but never postcondition. Is that because you...
Right. So assembly language is really continuation passing style, and there's no such thing as a postcondition here. It's one abstraction you can build on top if you're in that kind of mood. Yes?
So normally with postcondition reasoning, you have some connection between the pre and post, like logical variables or a relational postcondition. How does that manifest itself in this style of presentation?
By using higher order assertions about code pointers, like the return pointer of a function. And there will be quantifiers whose variables are in scope for both the precondition proper and the higher order assertion about the postcondition. And we define notations that make this look like the normal style, but are compiled to that.
This is all partial correctness, right?
Right, it's all partial correctness, it's only safety properties, the usual restrictions for most work in this area. Yeah.
Also a straight line, so there's implicitly some kind of liveness because you have to fall through the jump once you enter, right?
All the instructions are so simple that there's no interesting liveness. But you can write an interpreter, an obviously terminating interpreter for a single basic block.
But point two, to be sound, I mean, for total correctness would require rather more, because there's an implicit induction argument that goes on. So if you were to actually say, look, we're going to prove liveness, then you'd have to be more careful, right?
This framework would need to change to do liveness properties, and I don't have any insights into exactly how it would change.
Even if the termination of the programs is not so hard.
Yeah. All right, so that's the foundation of Bedrock, and on top of that, we're going to build up to languages and programming tools, sort of like the ones we're familiar with, but with this formal methods, correctness proof angle everywhere. So as one example of a layer of abstractions we can build, at the bottom we have the assembly language that I just introduced. We call it the Bedrock IL. Then on top of that, we have the Bedrock structured programming system, which lets you basically do macro assembly programming. Sort of looks like C programs. Then we have on top of that a language called CETO, which is another C-like language, but with data abstraction support built in and with a more conventional compiler than in the previous step. On top of that, we built a language called Facade, which is a very thin wrapper around CETO that is getting a little bit higher level and has a simpler memory model without any aliasing in it. Then we have Galena, which is the normal functional programming language of Coq. It's a pure ML-style language, and we're actually going to compile that into Facade and therefore push it down further towards assembly. And finally, we will produce Galena programs from Fiat, which is a language or a framework for program derivation that will let us start from relational specifications in higher order logic and connect to this framework where we will take those specifications and translate them to assembly programs with Coq proofs that the assembly programs preserve the meanings of the original specifications. And I'll make each of these layers more concrete as I step through the rest of the talk. And as I do that, I want to just keep returning to one example program, its life cycle as it goes through these different layers, and talk about how we reason about this program in each layer. So the example that I'm going to follow is, let's say we're calling some function f with two arguments 42 and 17. Here's some assembly code we might write for that function call. What it's doing is it's saving the two arguments in two stack slots. So the brackets are for memory dereference via a computed address based on the stack pointer register. We'll also take the address of this code label ret right after the function call, and let's store that in a return pointer register, and then jump to the function itself. So this would be how we would encode this in the calling convention that we came up with for Bedrock IO. And we would use a proof rule like this one to justify just the last of the instructions, the jump instruction. And the proof rule is saying, so first, this capital psi is our assumptions about which blocks of code exist in the program. And recall, every block of code has a precondition. Psi is a finite map that tells us for a code block address what is its precondition. So let's say we wanted to prove that P is a valid precondition for jumping to address F. What we have to do is look up F in the specification map, find its precondition Q, and then prove that P, the current precondition, implies the precondition of the function that we're jumping to. And this rule in its full generality would need to support indirect jumps, where the target of the jump is some computed expression. The rule gets a little more complicated, but not terribly so. And we would certainly expect that this function f relies on the more general rule when it actually returns by jumping to the value that we've stashed in the RP register. And the system supports that, but I won't go into the details here to avoid cluttering up the slides. So we can imagine that we have some precondition in mind for this block of code that would be annotated on the basic block that we're seeing here. So think of it as some higher order logic function from memory values and register values to predicates or propositions. Though it's a little more complicated than that in the way that these things tend to have to be when you have this combination of mutable state and recursive definitions and higher order stuff. And then this label ret is the beginning of a new basic block, and it itself has a new invariant that describes how memory should look after we return from this function call. And so these are the ingredients that we need to make all this work. All right, so let's move up to a higher level of abstraction. We have an extensible C-like language implemented within what's called the Bedrock structured programming system. And so the pitch for this system is based on the general idea of code generators, which we all know and love in the context of programming. Parser generators are a classic example where you can describe a language to parse in a nice, concise, formal language like context-free grammars. Throw it into your parser generator. Parser generator does the hard work of finding some C code that is going to implement this parser efficiently. Your C compiler produces assembly. And the great thing about this approach is that we are paying some performance cost for using a higher level of abstraction, but if it's a good parser generator, the performance cost is only applicable at compile time. It's what we pay while this parser generator is thinking and producing the C code for us. At runtime, we get, hopefully, code that is actually close to hand-optimized code in performance. Unfortunately, the downside is that conventional implementations of this parser generator box are hard to get right because they're doing ad hoc manipulation and generation of code, and the programming language doesn't provide much help in detecting bugs in that process. So another way of going about this problem uses a good idea called embedded domain-specific languages. For instance, maybe your parser generator is not, I don't know, a Perl script that uses regular expressions to munge strings and output strings. Maybe instead, it's a Haskell term of type grammar arrow C program, and now the Haskell type system is going to help you avoid certain mistakes. So what we're basically doing is we're taking advantage of the type system of the meta language. In this example, it would be Haskell, to guarantee properties of the translator in terms of how it works with code of the object language, which might be C in this example. So what can we get this type system to do for us? Well, we can get it to check basic syntactic well-formedness. For instance, if we represent code with algebraic data types, we can be sure we actually build syntactically valid code. We can get some help with checking variable binding patterns. And this would, for instance, take advantage of higher order abstract syntax or something like that that helps us get the compiler to check that there are no out-of-scope variable references. We can get the compiler even to do type checking for us using things like G80Ts in Haskell, where the type system of the object language is reflected in the type system of the meta language. And we might even want to try to get some help from the meta language in checking functional correctness of these code transformations. If we have a semantics in mind for the input language, we'd like to show that that semantics is preserved in the code that comes out. So that's what we do in the Bedrock system. And the big picture there is, so of course we're running everything inside of Calc. A program in this structured programming language is a functional program that uses dependently typed combinators to put together the pieces of a program. Think of these combinators as standing for things like if and while and function call and all of the features we know and love from C programming, but as libraries, not as built-in features of a language. And so when we run one of these programs, it produces some assembly code. And we can take that assembly code and translate it to all of the popular ISAs. But there's another way to run a program that actually produces the ingredients for a correctness proof in higher order logic. And this is things like verification conditions and the strongest postcondition calculators. And the goal in setting up this architecture is to make it possible for the programmer to use a set of combinators to build a program while not actually understanding how those combinators work internally. It should still be possible to verify a program by dealing with relatively straightforward proof obligations that hide the implementation details of a combinator. So the quick sketch of the formal details is that the Bedrock structured programming system is based on what we call macros, which are these code generating and formula generating combinators. And what a macro does is it produces a chunk, which is one of these control flow graphs inside an encapsulation unit. It has one entry point and designated exit point, and then arbitrary control flow inside. These are all assembly basic blocks in the middle. And also, conceptually, inside this box is, say, a verification condition that tells us what the programmer needs to prove for this to be a correct program. So we might call that chunk A. There might be chunk B produced by some arbitrary other sequence of macro invocations. And then we can give those as inputs to the if-then-else combinator, which then builds a new chunk that adds some new blocks and then drops in the blocks of the original inputs to this combinator and plums it all together properly. And we can take the verification conditions of the inputs and conjoin those together, add some new stuff, and now we have a new chunk built parametrically in the details of the two inputs. And we have our generic if-then-else construct without baking it into a programming language. And I'll leave out a lot of the details here, including exactly what it means formally to connect these control flow graphs together, the details of the other important dimension besides verification conditions, which is predicate transformers, corresponding to strongest postconditions, though we don't actually require that they be strongest. And also, there's a formal connection of all of this to Hoare logic that we use to justify the soundness of this whole system, so you don't have to trust it to believe that your verification means what you want. But I'll quickly connect this to the running example that I had of calling the function f on the arguments 42 and 17. So now we can actually write the function call that we meant directly instead of having to expand it into assembly. We don't have to write any program labels. And we still have a precondition before this function call and some sort of invariant afterwards that expresses how the state should look after the function returns. And we have to give rules that explain how to calculate a post condition and how to generate a verification condition for this call. The post condition rule is taking as an input this dictionary that maps program labels to specifications, and also the piece of syntax that we're verifying, and finally the precondition that we should assume as we go into this piece of syntax. This notation is meant to suggest we have a function call with some arguments, and we also have an invariant that must hold afterwards. So the proper postcondition of this call is just exactly the invariant that we said should hold afterwards. And the verification condition should be some formula whose truth guarantees that this is a valid program. And in this case, we have to say there exists some specification R which is associated with the function f by this map psi. So R is the specification of f. And then we say for all lowercase r, which is this is a first-class code pointer. When we look up the specification of R is the return pointer that tells the function where to jump back to when it's finished. That specification should be exactly this invariant that we ask to hold after the function call. So this used to be the precondition of the basic block of the return address. Now that pattern is sort of encapsulated inside this rule. So we have some return pointer R, whose specification is the one we asked for. And then we have finally this implication, which basically says, assume we're in some state satisfying Q, which is the precondition that held before the call, and then sort of symbolically execute the operation of storing all of the arguments in the stack and the return pointer in the return pointer register. This, any state that can be described by this sequence of operations is actually, it also satisfies the precondition of the function f that we're calling. So there's a fair amount of complexity in these few lines here, but the point is it's a relatively short formula, and actually we can completely automate proving conditions like this for concrete programs. And it relies on higher order logic, and we're also using separation logic under the hood here somewhere. Yeah?
Feel free to just bounce this question, but could it perhaps have extended psi with a mapping from R to P and then had the same as the rest of your constraints? But you didn't do that, and I wonder why.
Because that would reveal the implementation of the function call operation to the client code that's using it. That's how we implement it, but we want to expose a more general interface so that the programmer doesn't have to know that the return pointer corresponds to a new code address.
I mean, the quantification, the universal over all small r, it's really limited to the domain of psi. So, I mean, to prove that implication, you could just do case analysis and say there are only finitely many code points. Let me enumerate them all and check each one. But is that really what you want this thing to mean?
One complication that I've left out here is that these functions aren't really being passed psi, that it's actually internalized inside the language of predicates that are allowed to be used here. And everything is set up to support modular proofs where you're going to verify a code module without knowing the full universe of psi. And later you'll link it with others, and it should remain valid when passed pointers to code in those other modules. Right. And here's just a quick example of all these pieces in action. This is a program, its specification, and its proof inside of Calc. This code is processed by the normal Calc system, taking advantage of the extensible parser and the flexible dependent type checker. This turns out to be an implementation of imperative linked list length calculation. Here's the specification up here. I won't go into too much detail about what it says. It's using higher order separation logic and abstract predicates. Here's a predicate capturing the idea of a linked list, representing a mathematical list with a given head pointer. Now, next thing is a definition of the actual function, the calculate lengths. It has assignments, while, return, sequencing, the usual low-level imperative stuff. The only unusual thing for a programmer is the highlighted part here, which is a loop invariant that we use to generate verification conditions. And then down here is the proof, where we say this code up here is an OK module, and this proof is done in one line with automation from our library. VCGen tactic, you can probably guess what that does, generates verification conditions based on the annotations like this one. And then we call a tactic called sep that is a separation logic automation procedure for symbolic execution and entailment checking. It takes an argument called hints, which is a small set of lemmas we proved about the SLL predicate. And there's one other bit of tactic stuff here that we've defined in a few lines, but mostly this is an automated proof. The same proof works for a larger module that contains several more of your favorite list functions, and you can change the code and often not have to change the proof, yet you wind up with a proof from first principles about assembly language in the end. All right, so this is the end of this abstraction level. I just want to take a quick detour and talk about another language that we built on top of this one, which is a domain-specific language for XML processing and database access, which was used in that case study that I briefly said something about earlier. You can write programs like this. Again, this is code processed entirely inside of Coq. It's doing things like exposing an RPC notation and manipulating an in-memory relational database with delete and insert operations. It's running a kind of query over that database and running some command for each one. This happens to be an HTTP-based remote call to another server for every one of the iterations of the loop. This is all desugaring into a more general language for pattern matching on and generating XML, and as well as doing database access. We proved that this is a well-formed program, which is basically a type system level property. And then when we have this property, we can feed it into a compiler correctness theorem, which tells us that the code that will be compiled from this program is basically it's type safe. It maintains invariance on the states of data structures and will not trample over the state of other components of the system. And this compiler is actually implemented as one big macro in the structured programming system that I just presented. And the way the implementation is structured is we're going to do it in a feature modular way, where we will divide the language into different features and give each one its own macro, which could in theory be used in some remix of another programming language that chooses just a subset of these features and adds some others. And here's a quick diagram of the structure of the different macros we built. For instance, one that implements querying a database table, one that implements pattern matching in XML trees. Each of these has a separate encapsulated proof, and they can be composed together to build different kinds of languages that have the same level of verification support without redoing any of those proofs. All right, so let me tell you a bit about the language that we build on top of the structured programming system. It's called CETO, and the thing that it adds is first it has a more conventional compiler instead of just being a macro assembler, so it can support traditional program optimizations in the compiler, and it also has some support for data abstraction built into it, which is important for our motivating scenario, which is multi-language programming. So imagine we have programs in two different languages. Each of them has a verified compiler, where we mean compiler correctness in the usual sense, and each of these compilers produces assembly. We'd like to be able to link together the assembly programs that came out of the two compilers. Now, the wrinkle is each of the programs we started with has some kind of specification and proof. And these might be rather different if they're very different programming languages with different models. So how can we then get those specs and proofs to come together to accurately describe the linked program that combines these two pieces of assembly? And that's the challenge that we looked at in the design of this compiler. So imagine, as a practical example, language 1 contains an optimized data structure implementation with manual memory management for performance. Maybe think of this as C. And then language 2 it has the implementation of some intricate algorithm that uses that data structure, but really you want to think of this algorithm in a higher level notation. Maybe it's Java or something like that. So in more detail, we might have this program that has sort of the header file associated with the C implementation of finite sets of machine integers. We have some abstract type of sets, and we have operations to create a new set, deallocate a set. We can add an element to a set, add this key to this set, and compute the size of a set. And we can use those in some nice higher level code to write a function that takes in an array of integers as an argument and then is going to compute how many unique values appear in the array. And we can do that by allocating a finite set as a local temporary and doing a loop over adding all the elements of the array to the set, then computing the size of the set, deallocating the set, and returning the count that we found. So we'd like to be able to verify this program without knowing anything about the low-level language that provides the finite set data structure, and still be able to link code together and get a final theorem that this program meets the natural functional specification of counting unique values in the array. And the way that we do that is we use abstract data types with formal specifications as the glue between languages. So we don't want each language's semantics to have to say anything about the syntax or semantics of other languages. Instead, we use the preconditions and postconditions as the cross-language interface. So we have these precondition, postcondition, method invocation triples. So for instance, the set new operation has no precondition, and then on return it guarantees that the return value is a representation of the empty set. That's what this notation says. In general, the programmer can define new constructors like set for new mathematical domains that should be used in the specifications. The delete operation is sort of the opposite. There's a set at the beginning, afterwards there isn't. The add element goes from a set S to a set S with the key K added in, and the size operation preserves the set and also returns its size.
It's just that the language of preconditions and postconditions is sort of independent of the particular language, right? They're
Yeah.
somehow common across the system.
Right.
But there must be some place in which you have to say, look, if you've got a set built with these functions, you can't manipulate it with some other random thing in a different language that uses different representations, but still manipulates sets.
Right, so this set function is actually associated with a particular code module. It's not the general idea of sets.
It's a list set.
Yeah.
It's not just mathematical sets in general.
Yeah,
Okay.
sorry, I should have
All right.
been clear about that. So an implementation of a signature like this provides not just the code that implements these operations, but it also has to define what does this predicate really mean as a representation invariant that connects the abstract state, like the mathematical set, to the actual pointer-based representation of this data structure in memory. And different languages might have different ways of implementing this kind of concept. We still want to use a uniform abstraction mechanism for each of those languages. So returning to the running example of calling f with the arguments 42 and 17, now we have sort of two different proof rules that might apply to this call, corresponding to calls within the language and calls that might go to a different language. So this is, the conclusion of this proof rule is using a big step operational semantics for this programming language. I'll use sigma to stand for a local variable environment and mu to stand for a heap, which actually contains those abstract data type models like the set constructor from the last slide. And so this rule says if you're in this state of sigma and mu and you call f on these arguments, it will terminate and provide in this new variable environment and this new heap. And this rule says in the context psi, look up the function you're calling, find its definition. It looks like this. It has the number of arguments you're expecting in this body statement. Then let's run that function body s in the heap that was active at the time of the call and in a variable environment that maps each formal parameter to the value of the actual parameter in the caller. That's all this notation says. And this will produce some new local variable environment and some new heap. We copy the heap down to the result of the call, but we throw away the local variables and just in the caller, we let it keep its original local variable values. So this is just a standard operational semantics kind of way of defining a function call. So we'll call this kind of mapping of the psi function an operational spec. And we use this mapping for calls within a language. But what's more interesting is the other case for calls across languages, where the psi mapping might also say this function is associated not with code, but with a precondition and a postcondition, expressing the contract for using it. And now we can say the way to evaluate this call is check that the precondition P holds of the argument values and the initial heap, and then non-deterministically pick a new heap, mu prime, and check that the post condition holds of the argument values, the starting heap, and the final heap. And then we copy the final heap down here as the result of the function call. So this is a kind of mixed operational and axiomatic semantics to let us stay operational when we're within one language, and then take these axiomatic steps to model the interface between languages. And remember that these P and Q predicates can be talking about abstract data types through these constructors like set, and that lets us reason about calling an external function without knowing the implementation details of how it represents things in memory. Because all the abstract predicates have formal definitions and separation logic somewhere, but our proof can be parametric in those. All right. So I think I'll skip through some of the details of this slide, but it turns out that we can use that semantics to state a traditional compiler correctness theorem in terms of a Hoare triple that every invocation of our compiler should satisfy. And what we do is we translate this kind of Hoare triple into a precondition for the assembly code that we output by our compiler. And basically, the compilation correctness theorem works in terms of showing that every assembly program that comes out has a derivation in an appropriate logic. This logic supports semantic linking between modules. Therefore, we get for free that we can link the outputs of different compilers that follow this kind of strategy, because the final theorem or formal interface of a piece of compiled code is independent of the compilation details. It only focuses on the interface as accessible by other programs or other modules. All right, so we add another language on top of this one called Facade that is exactly the same syntax, but has a slightly different operational semantics. So recall that the old one had this explicit notion of a heap mu in the semantics. Facade has, as its state, exposes only the values of local variables in a function. And though local variables that store abstract data type values will be represented in the end with pointers into the heap, we will hide that fact in the definition of the Facade language by imposing some extra rules. So now when we run a function call, I'm just showing the axiomatic case of the semantics. It says check the precondition on just the variable values, no more heap involved. Check the postcondition on before and after versions of the arguments to the function. And furthermore, we can't allow the same variable to appear twice in this list, because that would create aliasing in the callee function. And to preserve the fiction that all the state is in the local variables and they're all these nice, well-behaved things like finite sets, we have to prevent aliasing from ever coming up. So by adding restrictions like this one that will prevent anything that would create aliasing in the implementation, we can allow the programmer to pretend that the variables really are directly storing finite sets without having to expose any concept of pointers or aliasing. All right, and the last steps of this picture are we extend up to compiling functional programs to that Facade language, which is fairly close to functional programs compared to where we started. And we'll also derive functional programs from specifications at the very top level of this picture. So we have this framework called Fiat that does that derivation process. It's applying a well-established idea called program derivation by stepwise refinement. So what we do in general is we write a mathematical specification written to be as clear as possible without worrying about performance. Then we apply what we call optimization scripts that refine that specification into an efficient program. And the refinement process is generating proofs that witness the correctness of the derivation and show that the final program really has the specification we started from. And compared to past work in this area, we're focused on achieving both high levels of automation in program derivation, but also high assurance about the process, where we have a very small trusted code base to check the final theorems. So briefly, we can start with code like this, which is an SQL-style query over a data schema that I haven't shown here. Like in earlier examples, this is all parsed and type-checked inside of Coq. So that process will tell us if we have any errors in referencing non-existent fields in tables or something like that. It's using a syntax for database queries inspired by monadic query comprehensions. And then, so this is our spec. It's not actually executable directly. It desugars into set theory kind of specifications. And now we have to say, how do we implement this efficiently? And we do that by writing an optimization script, where we basically start by suggesting a data structure to use to represent each one of the tables in that database. This is similar to specifying an index in standard SQL, but we do it by using first dependent types that tell us that this is the type of a correct index implementation for this relation from our specification. And then we run a tactic in Calc that builds the data structure and also the proof that it's a sound representation of the specification. So we do that for both of our database pieces. Then we define an abstraction relation that explains the connection between the specification and the data structures that implement it. And then we just pass that relation to a tactic from our library called plan, meant to evoke the idea of query planners in SQL. And then this tactic will build the efficient functional program for us, just using the hint that we gave by suggesting a data representation. And in particular, the code that comes out is like this. It's a standard functional program using old favorites like fold left, and at appropriate points also calling methods like bfind and bcount, which are for a data structure from our library that implements these indexes as nested AVL trees. So we get good asymptotic performance from this code. And of course, we also generated a proof that it preserves the behavior of the original program. And the basic framework this all happens in is representing computations as sets of possible values, or we're in a non-determinism monad or a power set monad, where we have the usual return and bind combinators that we can define in appropriate ways. For instance, return is just the singleton set constructor. Bind uses quantifiers in the right way. And it turns out that in this setting, the subset relation serves as a natural notion of implements. Our original specification can be a very non-deterministic program in this monad. The final efficient program can be a very deterministic program that has just one possible value. We will gradually refine the spec into the efficient program step by step. So for instance, if we know that our specification is we want some number x that is even, we can run one step of refinement and replace that goal with we've chosen some predicate p, and now what we're trying to do is pick some value n that satisfies p, and then return 2 times n. Obviously, because we're returning 2 times something, this is a correct implementation of evenness. So we can refine the specification like this, potentially reduce some of the non-determinism, and then repeat that process until we get to a term that has just one possible answer. And it also turns out that this subset relation is a preorder and has the right congruences, so we can treat it as an oriented relation for rewriting. So for instance, if we start from the step we reached on the previous slide, if we have a fact that the set of x such that p can be implemented with the set of x such that q, we can rewrite within this big formula, replace the x such that p with x such that q. And so in general, our derivations are just sequences of steps like this, applying rewriting rules within the terms that we use to summarize what we know about our goal. And eventually we get to a point where the whole term is just return something. It's a deterministic program, and we can just run that in Calc or even OCaml, which we extract to. So that's the big idea. We write scripts that automatically find the right rewrite rules to apply for different specification domains, and thereby we produce programs in Galena, the functional programming language of Calc, and we can extract those to OCaml to run them. But we might be able to get even better performance by going through Bedrock and actually trying to produce assembly programs from the Galena programs that we synthesized. And what we do for that is we reuse the refinement framework to, given a functional program, find a C++ style program in our facade language that has the same semantics as that program. Then we can use our verified compiler to lower that to the C-like level of the CTO language, and the verified compiler there to produce an assembly program, which is one of these semantic modules that Bedrock supports. And then we can also say implement a B-tree data structure more manually in one of these low-level languages, do a more manual proof that it meets some specification of an abstract data type, and then we can link together our verified B-tree with the synthesized code, and we can get a closed program with a proof that this combined assembly code actually meets the specification that we started with here. And this whole pipeline, accepting this data structure that we built manually, this pipeline is automated while still generating a proof from first principles. And just briefly, I'll flash up some examples of what different stages in this derivation process look like. We can start out with a relational specification like this one, which captures the idea of computing the sum of the unique elements of a list. This harpoon down operator is for computing the set of elements of a list. And we can fold the plus operator over that set and get the number of unique elements in there. We can translate that to an executable functional program that uses a finite set as an intermediate data structure, much like in an example I showed before. An important thing about this code is that it uses some implementation of the finite set abstract data type. The proofs are all parametric in what that implementation is. So we record that this code is dependent on some finite set implementation. We can then translate the code to a C++ style program that does a similar thing using a while loop instead of a fold left, with allocating a new finite set and doing imperative mutation and deallocation of both the set and the list at the end. Still has a finite set dependency. We can compile that to an assembly program that maintains the same dependency. And then we get a final theorem in separation logic saying that the specification for this function is that it starts out, when you call it, there must be a linked list in memory starting at the argument L. And in a disjoint part of memory, there must be the data structures of the malloc library. And then afterwards, the return value R belongs to the set of legal answers that our original specification dictates, and the malloc library state is still there. And so we can take a verified implementation of finite sets at the low level, and we can link it with our assembly program and get the code and the proofs for this closed program showing that it really does implement this specification. Right, and I think I'll probably skip the details of this slide, which just explains a little bit about the internal process of deriving a C++ style program from a functional program using the same refinement framework that we used to get the functional program in the first place. We just have a notation for state arrow state means the set of programs that would transform this state to that state, and we can use the specification, use the functional program to write down an initial description of this state and then keep refining it into sub-computations until we get to the point where all the steps are actually constructs that the target programming language supports. And we've done this in a way that where we have a proof that the final program really preserves the behavior of the original one. All right, so I think I'll wrap up here. This is a URL for the website for our project on the web. It's released as open source. Quick summary of what Bedrock provides. It's a small trusted code base for doing proofs of functional correctness. It supports modularity and proof automation and verified compilation, all for one common assembly language that with the possibility to write programs and derive programs in many different higher level languages. Thanks.
Okay, thank you. We're running a little late, but time for a couple of questions.
A couple of slides back, you said about the performance versus of the extraction into Camel versus going through your toolchain. Is it faster, or have you sort of actually got any numbers there? Or
I think we haven't done all of the engineering work yet that would be needed to make it actually faster, but
neither is the OCaml extraction people either.
You think the OCaml extraction in Coq hasn't been optimized much? Okay, that could also be true. In theory, it seems obvious that it should be able to be faster, but we haven't actually demonstrated that empirically yet. Yeah.
So one of the points of lowering abstraction is to do more optimizations, right? So you want to do register allocation and stuff to keep stuff from registers and stuff. So have you done any of that work, or are you just producing cookie cutter code from each level to each?
We don't do register allocation yet, but we do constant folding and dead code elimination as two token examples we picked in our verified compiler for the two directions of data flow analysis. Other directions should be compatible too, but we haven't implemented or verified them yet.
One question.
Yeah.
Yeah. So when you went from the Galena down to the C++ or whatever it's called, you're actually inserting memory management there, right? Because you were deleting. So how do you justify those steps? Because there isn't anything about memory management in the high-level code at all.
Right. So we have to prove lemmas like this one that characterize how to implement functional programming constructions in terms of lower-level idioms that might involve memory management being introduced explicitly.
Okay. Are these all like kind of people optimizations almost, or are they?
Well, the whole compilation process is just applying this kind of rule. So here's one for fold left, and there might be others for other kinds of operations.
Okay, Adam's around today and tomorrow.
Right.
So grab him when you can. And I think he'll be coming to the meeting at midday as well. Okay, thanks again for
Thanks.
very interesting talk.